All right, in this video, we're doing part 3 of assignment 11, my Calc D multivariable class. We're going to be finding a potential function, or we're going to show that our vector field is not conservative. All right, so let's look. Number 7, the vector field is z, and then 1, and then x. So z1x. So this is partial x, partial y, partial z. So what I'm going to do is I'm just going to integrate partial x with respect to x. And so that's going to give me that my function, my potential function, would be xz plus some function of y and z, right? Which would just, when you take the derivative of a function of y and z, it'll be 0 with respect to x. So we have this. Now what I'll do is take the derivative of this with respect to y. So if I take the derivative of this with respect to y, I just get that it would be partial y of g, that function of y and z. Now I'm going to compare to what I'm given as partial y. So this should be equal to 1. From here, I can integrate with respect to y, right? Because it's partial y, so integrate with respect to y. That's going to give me y plus some potential, sorry, I shouldn't say potential because we're finding a potential function, plus some arbitrary function of just z, right? Because the derivative of a function of just z with respect to y would have been 0. So now let's update what we think our potential function is. So g we now know is y plus h of z. So we have xz plus y plus h of z. I'm going to take the derivative of this with respect to z, and that'll give me partial z is x plus h prime of z. Now compare this to what we think partial z is, which is just x, which tells me that h prime of z should be 0, right? Just subtract x from both sides. And so if h prime of z is 0, then there is no function of just z. So we can say a potential function is xz plus y. That's basically what we're going to do, and we're going to do a ton of them. So let's take a look at the next one. So our vector field is xz, nope, it's x0y. And remember, that's partial x, partial y, partial z, if this is the gradient of some potential function. We're looking for the potential function. In this case, I'm going to start off with partial z. So it kind of doesn't matter where you start. I'm just starting here because there's a y there, which means I think that partial y shouldn't just be 0, right? If there's a y in partial z, that means that we have like z times y, and when we find partial y, we shouldn't have had 0. So I'm looking ahead, but again, if you don't look ahead and you just kind of do the same algorithm every time, it'll work for you. You can just kind of skip some steps sometimes. So I'm integrating partial z with respect to z, which is going to take me to a potential function of yz plus some arbitrary function of x and y. Now, if I find partial y of this, because that's what I'm hunting for at this point, partial y of this should give me 0, but partial y of this gives me z, which is not 0. So there actually is no potential function in this case. So what I'm going to do is I'm going to use the tried and true method of showing there's no potential function. I'm going to calculate the curl, which is this determinant. So it's ijk, partial x, partial y, partial z, and then f, our vector field, so x0y. So I'm just going to calculate it, right? It's I, and then you do partial y of y minus partial z of 0. So we'll have this, and that's going to give me 1 minus 0. Then it's minus j times partial x of y minus partial z of x, but that's just 0, so it's minus j times 0. And then plus k, and when we do that, it's going to be partial x of 0 minus partial y of x, which is 0. The key thing, though, is that the first component was not 0. We need to get 0 if there's going to be a potential function, so there is no potential function, which means f, our given function, is not, our given vector field, I should say, is not conservative. All right, let's take a look at the next one. So here's our field. It's y squared, 2xy plus e to the z, y e to the z. So we're going to try to find a potential function for this. I'm just going to label these partial x, partial y, partial z, integrate partial x. So when I'm not sure what's going on, I always just start with partial x, integrate it, differentiate with respect to y, blah, blah, blah. So that's what I'm going to do. Integrate y squared with respect to x will give me xy squared plus some arbitrary function of y and z. Now I'll take the derivative of what I think the potential function is with respect to y and do a comparison. So this will give me 2xy plus partial y of yz of g, right? So partial y of g. Now compare that to what we think partial y is. So partial y is given to be 2xy plus e to the z. Subtract 2xy from both sides. So our partial y is going to be e to the z. So now what I'll do is I'm going to integrate this with respect to y, which gives me that g of y and z should be y e to the z plus some arbitrary function of just z. So now I'm going to update what I think my potential function is. I now think my potential function is xy squared plus y e to the z plus h of z. I'm going to take the derivative of this with respect to z, right? Find partial z and compare with what we were given. So the derivative of this with respect to z is y e to the z plus h prime of z. Compare with what we have. Partial z we're given is y e to the z, which means that h prime of z is just 0. So our potential function, or a potential function, is xy squared plus y e to the z. So the same thing every time. Sometimes you can skip a step because you notice that something's a little bit off between like partial x and partial y, or partial y and partial z. Who knows? But that's what we're doing. Let's take a look at the next one. So our vector field is y, x, z cubed. So if this is the gradient of a potential function, if this is a conservative vector field, that'll be partial x, partial y, partial z. I'm going to integrate partial x with respect to x, and that'll give me xy plus arbitrary function of y and z. I'm going to take the derivative with respect to y, so find partial y. That's x plus partial y of g, and compare to what we think partial y is, which we think is just x. I mean, it's given, that's x. The question is it actually partial y of our potential function? So that would mean that partial y of g is 0. And that means that really we can update what we think our potential function is to just be xy plus some arbitrary function of z. There's definitely not an arbitrary function of y and z, but maybe there's just one of z. Let's take partial z of this. So partial z of this is just going to be h prime of z. Compare to what we have, partial z in our gradient, or in our vector field, we don't know it's a gradient vector field yet, is going to be z cubed. So if I integrate this with respect to z, I get 1/4 z to the 4th. Update what we think f is, and we have xy plus 1/4 z to the 4th. So this is a conservative vector field, and we found the potential function. All right, let's look at the next one. We've got f is cosine of xz, comma sine of yz. So that's suspicious, xz and yz. And then xy sine of just z. So there's no way when we take derivatives that we go from sine of z to suddenly cosine of xz or sine of yz. So I'm thinking there's no way that this is actually a conservative vector field. So what I'm going to do is I'm just going to go for it. And my basis for that is that these would have to be partial x, partial y, partial z. This is problematic. That's sine of z, right? There's no way to go from sine of z to cosine of xz. Like, it's not going to magically happen. So I don't think this is conservative. So I'm going to jump right to finding the curl of this thing. So I set it up, and now I got to actually do it. So it's going to be I. And then we do partial y of this thing is x sine of z. And then minus, we do partial z of this thing, which is going to give us y cosine of yz. And that right away, that's not 0, right? So we already know not conservative. Let's keep going, though. We would have minus j. We'd have to do this and this, right? So it's partial x of xy sine of z, which is just y sine of z, minus partial z of cosine xz, which is negative x sine of xz. This is also not 0. And then if we do the last one, it's plus k, and you have partial x of something that doesn't have an x in it minus partial y of something that doesn't have a y in it. So you actually do get 0 for that one, but it doesn't matter because you're not getting the 0 vector, which means this thing is not conservative. So this is not a conservative vector field. All right, let's look at the next one. f is cosine z, y is, f is cosine z comma 2y comma negative x sine of z. If you don't really think about how you read these things, you read them incorrectly, obviously. I'm doing that constantly. All right, so it would be partial x, partial y, partial z. If it is in fact conservative, we're trying to see if it is, find a potential function. I think this will have a potential function, so let's do it. I'm going to integrate partial x with respect to x, which gives me x cosine of z plus arbitrary function of yz. That's kind of the key, is putting in the arbitrary functions as you go. Find partial y of this thing. So x cosine of z doesn't have any y's, so we're just going to get partial y is partial y of g, that function that we created, the arbitrary function. Compare it to what we think partial y should be, which is 2y. So now we just integrate this with respect to y, which will give us that g of yz is y squared plus an arbitrary function of z. Update what you think your potential function is. So now we think our potential function is x cosine z plus y squared plus h of z. Find partial z of this. So partial z of this is going to be negative x sine of z plus h prime of z, because the derivative of y squared just is 0 with respect to z. Compare to what we have for partial z. We have that partial z is negative x sine of z, which must mean that h prime of z is 0. So update what we think a potential function could be is x cosine of z plus y squared. All right, we're going to do one more in this video, and then we'll be back to do the rest of these. So our vector field that we're given, which may or may, I want to say it's potentially conservative, but that's a bad idea, right? Because we're finding potential functions. So this may or may not be conservative. We're going to figure it out. So if so, this would be partial x, partial y, partial z. I'm going to start with z because I think it has the most going for it in terms of working this out, right? It has a y, it has an x. And I think that if I integrate that with respect to z, I'm going to be well on my way to solving this problem. So again, I don't know, you just do a lot of them and you get that sense. And if you're not sure, just start with partial x and always do the same thing as I've mentioned before. So I'm starting with partial z. I'm going to integrate that with respect to z. Gives me y times z plus z times tan of x plus an arbitrary function of x and y. So I'll find partial x of this thing. Partial x of this gives me z secant squared of x plus partial x of g. It's a lot of saying things, which is what I think I'm stumbling over. Compared to what we think partial x is, which is 2 secant squared of x, would tell us that partial x of g is 0, right? It's not contributing anything. So we say partial x of g is 0. Now I'm just going to go back to this. I don't have to update anything really. I'm just going to find partial y of what I think our potential function is. Partial y would just be z plus partial y of g, our arbitrary function, compared to what we have for partial y in the event that this is conservative. And it would just be z, which means, again, partial y of g must be 0. So actually, we found our potential function by starting with partial z. We just found it. It was there. A potential function for this is yz plus z tan of x. All right, I'm going to stop this one here. I'll be back in the next video to finish off this particular problem set. Hope this was helpful. Good luck.